Hello, we are Group 7 from SC4000, and today we will present our project about machine learning. Here is the content of our project. And we are doing cassava classification.
Here we see the dataset of 21,397 images distributed across 5 classes with a clear imbalance. Label 3 dominates with over 60% of total data, while label 0 accounts for just 5%. To address this, we use two approaches, one with balanced data ensuring equal representation for all classes, and another that kept the original imbalanced distribution to reflect real world conditions. First, we address the class imbalance by creating a balanced dataset. A validation set of 500 samples was created with 100 images sampled from each class. The remaining 20,897 images were allocated to the training set. To balance the training data, all classes were downsampled to match the smallest class size of 987 samples, ensuring equal representation across all classes. This helps the model learn effectively from all classes and reduces bias. The chart shows the balanced distribution for the training and validation sets. Here we show the train validation split, preserving the original class imbalance. Train set with 95% of the data and validation set with 5% of the data. This approach simulates a real world scenario with imbalanced data, helping us evaluate the model's performance without any balancing techniques. The chart illustrates the distribution for both sets. This slide highlights the data augmentation technique used to enhance the training data set. Steps included random rotation, resized cropping, flips, and color jitter to improve variability, along with two tensor and normalization to prepare the images for the model. The examples on the right show how these transformations enhance diversity in the training data. Simpler preprocessing is performed for the validation dataset to ensure consistent evaluation. Steps included resizing, center cropping to preserve image content, converting to PyTorch tensors, and applying normalization for consistency with training data. The images on the right illustrate these steps on validation sample.
In the next few slides, we'll discuss an extension to our preprocessing, and it is a technique for removing noise to our images. So a recurring problem in the dataset is that a lot of images contain noisy backgrounds, and these noisy backgrounds contain dirt and potentially leaves from other species, which would actually affect the classification of the subject of the image. And so actually to tackle this problem, we're using a combination of grounding dino as well as the segment anything model. The grounding dino is a vision language model that generates a bounding box based on a text input. And the segment anything model would generate a segmentation mask based on the output of grounding dino. So the way the segment anything model works is that you take an image, and in our case, it would be a leaf, and it would be passed to an image encoder to generate image embeddings of that image. At the same time, we'll pass in the bounding box that was generated from the grounding dino, which would be passed to the prompt encoder and passed to the mask decoder along with the image embeddings to produce the segmentation masks. And to demonstrate what this would look like, here we have a natural text prompt that we pass to grounding dino, which is a photo of a leaf. And grounding dino would output a bounding box of this object, which would be passed through the segment anything model to generate the masks as shown on screen.
Now, let's talk about model construction. Given the high complexity of this classification problem, we decided to fine-tune multiple models individually and integrate their results. In the current environment, visual transformer naturally become our first choice. Through experiments, we found that increasing the model size and the resolution effectively enhance the model's performance. Therefore, we choose VIT large with a resolution of 384 for our first pre-training model. To achieve diversity in model architectures, we selected our second model, ConvNext. The authors of ConvNext believe that convolution networks are not outdated and can achieve excellent performance after being modernized. Through our experimentation, we found that while increasing the resolution is beneficial for the model, enlarging the model size does not significantly improve performance on this task. Therefore, we decided to use the base model with a resolution of 384. And finally, we selected CropNet as our third pre-training model. This model is fine-tuned on MobileNet with plant disease knowledge. However, this model is built with TensorFlow. So for training this model, we need to use Keras. Next, we try to define the loss function. Considering that this task involves extensive professional knowledge, label smoothing is introduced to improve the model calibration and reduce overconfidence. And as the dataset is imbalanced, we proposed another loss function by emphasizing the minority classes with a weight. However, we found that adding weight actually reduced the model score on the final benchmark. This indicates that the benchmark itself is imbalanced, and adding weights prevented the model from learning the original data distribution, leading to a lower score. So we adopted the first function as our loss. As for our fine-tuning details, we utilize Hugging Face trainer and weight and bias for efficient training and monitoring. We applied different learning rate schedules for different models. Since we conducted extensive experiments during model selection, we initially used LoRa, which allowed us to train numerous models simultaneously in minimal GPU resources. For the final training, we employed DDP to enhance training efficiency. All our models have been open sourced on Hugging Face. And finally, we proved the necessity for image transformation by experiment. We can find that there is a significant overfit in the training process of the blue line. Image transformation makes the training set harder, so the model can learn more from the data.
Hi, I'm Sian, and I will talk about our group's merging strategies. Firstly, we constructed confusion metrics for these three models. Overall, we found that convex next V2 performs better, but not in all the cases. We found that different models, they may have different behavior on different labels, and they can somehow complement with each other. For example, convex V2 it performs better in label 0, 1, 2, 4, and CropNet and VIT performs better in label 3. Thus, we have a simple idea. Can we somehow merge the results together? The result is yes. There are two kinds of merging strategy, hard voting and soft voting. Hard voting is simpler. It directly gets the predicted categories as input and using majority voting as fusion method to predict the final output. However, it ignores the confidence levels of the output and sometimes may behave even worse. Another method is soft voting. It gets the probability distributions of different outputs. Thus, it can utilize the confidence levels and perform better in both validation set and the test data set. However, let's think about some further improvements. We have two simple observations. Firstly, a more extreme probability result it means that the model is more confident about the result. Secondly, if a model is more confident, we should assign a greater voting weight to them. For example, let's consider such a case. For input, both model A and B they predicted as category 0 with 0.5 probability. Model C predicted as category 1, which is 100% sure. Then, which is the result, 0 or 1? In both hard voting and soft voting, which we explained before, it is category 0. However, it is more possible to be category 1, since model C it is 100% sure, while A and B is unsure about them. Then, this is the main idea of the confidence from the predict probability. For more extreme values, we will believe it more. A probability closer to 1 or closer to 0, it should have more weight compared with probabilities closer to 0.5, because they are more confident whether it is correct or wrong. Then, we can give some definitions about the confidence level. Firstly, C0 should be equal to C1 as 1 because they are 100% sure. Secondly, C it should be a continuous function in 0 to 1. And thirdly, C should be a quasi-convex function, which means that if we take two values of them, the median of them should be smaller or equal than the maximum of the two values. Thus, we choose such a CP as our confidence levels from the probabilities. Based on that, we can have a new voting weight. We can also say that the soft voting is just a special case which chooses CP, which is always equal to 1 in this voting weight, and we get our final votings. We also test this kind of voting in the validation set and test data sets. It shows that the result it is much better.